So just a quick review of what we have been discussing so far. We introduced the idea of differential amplifiers. Then we mainly compared two kinds of biasing in differential amplifiers. The shown on the left here is a voltage bias differential pair, and shown on the right here is a current bias differential pair. And we discussed how to find voltage gains for both these structures. And we saw that the common mode, the differential mode gain for both these amplifiers, both these differential pairs, was same and given by Cmrr. Because if you see, this node will come to differential AC ground, this node will also come to differential AC ground. So therefore, the half circuits from differential mode point of view is exactly the same. Therefore, the gain is also the same. The next thing we discussed was the common mode gain. We said this, since we are connecting a voltage source at the source terminal, this node is at AC ground itself. It's not necessarily for that node to come to zero or for that node to be at different at AC ground. You don't necessarily have to apply differential signals. As if any for any small signals that's applied to this amplifier, this node is actually a hard AC ground because it's connected to a voltage source. So therefore, it cannot have any small variations. So because of that, we saw that the common mode gain was very high, and that was almost as same as your differential mode gain. On the other hand, when you look at this circuit, we discussed how to find the common mode gain for this circuit. We said since the sum of the two currents has to be constant, and the way in which this differential pair operates is that the sum of the two currents is constant. So we called it I1 and I2, and we said I1 plus I2, the small signal variations is 0. I mean, if I write capital I1 plus capital I2, that is equal to I. This is the large signal current, should always be equal to I. Small I1 represents to the change in I1, and small I2 represents here the change in I2. We said the sum of I1 plus I2 equals 0. But since both the gates are increasing, that's why we measure common mode gain. You increase both the gains and try to measure what will be the change in the currents I1 and I2. And we said the only possibility is I1 and I2 equal to 0, which means there can be no change in the drain currents for common mode inputs. Therefore, we said both the output voltages, small signal variations will be 0. So therefore, ACM was 0. So for a current bias differential pair, we said ACM was 0. And then we also said ACM DM, it's nothing but the differential mode gain for common mode inputs is 0 for both the circuits because the circuits are symmetric. This is a measure of symmetry. As long as the circuits are symmetric, we said ACM DM will be 0 for both the circuits. The difference, however, here is in the common mode gain. So they behave very differently as far as common mode is concerned, ACM is concerned. The voltage bias differential amplifier offers a really large common mode gain, whereas a current bias differential pair offers a very low current common mode gain. And we said for this reason, we prefer a current mode amplifier, a current mode differential amplifier. Then we introduced mismatch between the two transistors. So 1 and 2, we assumed that no longer there was a differential symmetry around some center axis. In that case, we analyzed differential mode, common mode, and ACM DM in the presence of mismatches. And we showed that approximately the differential mode gain will be very, assuming that your change in delta GM and delta R are much smaller than GM and R respectively. If we make this assumption, then we said the differential mode gain will be very close to GMR itself, in both the cases. And the common mode gain was also very close. Here said, this is something we said was an interesting point, is that by biasing a differential pair using a current source, we are naturally enforcing a differential operation because the sum of the two currents, I1 plus I2, the small signal changes in I1 plus I2 should always be equal to 0, which means we get this condition I1 equals minus I2. So we said if you use a current source to bias this amplifier, we are somehow inherently enforcing some kind of a differential operation. So because of which we found ACM to be 0. So even though there is mismatch between the two transistors GMs are not the same. If you try to increase both the gates by same amount, The only possibility, the only possible solution that this circuit can permit is when I1 and I2 are individually 0. Both cannot increase. If one increases, the other has to decrease. So because of which we found ACM to be 0 for this circuit. Even in the presence of mismatch, we found ACM to be 0, and we said therefore ACM DM will also be 0. And then we discussed another important, then we discussed ACM DM for this circuit here, ACM DM, which we said was a fraction of, so delta GM by GM times GMR. So we said ACM DM was a fraction of where delta GM by GM is the fractional error or fractional mismatch between the two transconductances. If you have resistor mismatch also, we said it will be delta R by R into GMR. Okay, so then we said ACM DM can be written as ACM common mode gain times the fractional mismatch in both the components, delta GM by GM plus delta R by R. So this is what we discussed about this, the small signal common mode and differential response in the presence of mismatches. Then we introduced a bit more of non-idealities in the circuit. What we said is that if you consider this current source to have a finite output resistance and let output resistance be RCM, in that case, how do we analyze the circuit? I mean, this is a circuit with already mismatches present. So 1 and 2, the halves are not identical. And now we can assume, what if the current source has a finite resistance? And we said that in that case, even now, to analyze the circuit, we will still use the half circuit concept because it makes the analysis easier, but I'm going to analyze both ends, not just one half, but I'm going to analyze both halves. But using half circuit concept, the idea of half circuit makes the circuit analysis simpler. So we said, even though there is mismatch between the two pairs, two halves, the transconductances or the load resistances, we argued that since that mismatch is so small, that I can assume this node to be very close to differential ground. When you're doing a differential half circuit analysis, we said it can be assumed very close to differential ground. So this approximation, we called it as quasi-differential approximation. I can still assume that node to be very close to AC ground, and by making that assumption, the analysis becomes very simple, and we said that's a quasi-differential approximation. And the differential mode gain was very close to GM times R. In this circuit, differential mode gain is GM times R. And for common mode gain, again, we did the similar quasi-differential analysis, and we showed that the common mode gain is GMR by 1 plus 2 GM RCM. Here, I'm assuming lambda is 0 or R naught is infinity. So then we said it reduces to this if you draw the equivalent circuit. So this will be 2 RCM, and the drain resistance is R. So you are supposed to find the gain from Vi to V naught. It was simply equal to GM bar by 1 plus 2 GM RCM. And GMR is nothing but a DM, differential mode gain. So what we noticed here is the common mode gain for this circuit was a DM, the differential mode gain, divided by 1 plus 2 GM RCM, which is GM RCM can be quite a large number because this is supposed to be a current source, so RCM will be quite large. So the product GM RCM will also be quite large. So the common mode gain, in this case, even though there was a finite common mode gain, it was still much smaller than the differential mode gain. Then we showed ACMDM for this. ACMDM, we showed it as ACMDM, we showed it as this is ACM, ACM in the current biased case, multiplied by the fractional errors, delta R by R plus delta GM by GM. So you can refer to the proofs. It is a very straightforward proof. We showed that ACMDM will be equal to ACM times the fractional mismatches in both the load and the transconductances. Okay, so this is what we concluded in the previous lecture. So I missed one point in the previous lecture, so I'll just discuss that now. One very important point. So we said ACM-DM is a very useful metric. It tells you how symmetric a differential amplifier is. Ideally, ACM DM should be equal to 0 for a purely differential amplifier. ACM DM should be exactly equal to 0. Now, in circuit or most analog and RF systems, generally we define a parameter called signal to noise ratio. So most circuits exhibit noise. I mean, most circuits uh, have noise associated with them. So we define a parameter called signal to noise ratio. It's a metric that tells you how good the system is. For example, if I'm talking about an audio system, there can be some ambient noise. If the audio signal is very low or equal to the ambient noise, then you won't be able to hear the signal very well. So there will be some noise level here. You want your signal level to be much higher than the noise level. So normally we take the signal power divided by the noise power, V by N. So this term is what we refer to as signal to noise ratio. It's a metric of how good the system is. If your noise is very low, your SNR will be very high. Or if your signal power can be, see, for the same noise, if you have a much higher signal power, even then your SNR will be very good. Okay, when I say signal to noise ratio is very good, you will be able to hear the signal better than the noise. Your signal will completely dwarf the noise. Okay, that's a sign of a good system. Similarly, we'll try to define another parameter for a differential amplifier system as well. So the whole idea of a differential amplifier system is that if I apply an input signal Vi and take the output differentially, so can I say your V naught equals A dm times Vi? See, this is the desired signal. You're applying a differential input signal and taking the output differentially. A dm is your differential mode gain. So then V naught equals A Vm. So A dm times Vi, this is your output signal. Now for a differential amplifier, any common mode signal is noise. Any common mode signal is noise. So if I apply a common mode signal and measure the differential output, this is, see, the ideally differential system should not respond to any common mode changes. So when I'm going to apply a common mode input, now here I'm applying the same input to both the terminals. Here previously in the first example, I applied the input differentially. Here I'm shorting the two inputs and applying the same input. This is a common mode input. For a common mode input, your output should not respond as well. But in the presence of mismatches we just saw, it's going to respond. How can you write your output as in terms of Vi? So if Vi is the common mode input, what will be V naught in terms of Vi? Is it ACM times Vi or it's ACM DM times Vi, right? It's not ACM. I'm taking the output differentially. If I took the output from a common mode point of view, yes, then it is ACM, but it is ACM DM times Vi. Right? See, that's how I measure ACM, right? So how do you measure ACM? How do you measure ACM? You apply the same input to the differential amplifier and you're shorting the outputs. That's like taking average. So you're shorting the outputs and measuring it. That's how you measure ACM. Okay? Whereas ACM DM is measured this way. You apply a common mode input, but measure the output differentially. So that will be ACM DM times Vi. See, for a differential system, this is what matters. This is what matters for a differential system. ACM won't matter. Okay? ACM DM is what that matters. But ACM DM will have a weak dependence on ACM, but let's ignore that. But when I talk about differential system, I'm always taking my output differentially. So now this is the signal. What I've applied here, Vi, when I'm taking the output differentially, that's the desired signal. This here is noise. So similarly, we define a parameter while taking, for a differential system, a common mode response is like a noise response. So therefore, if I take the output ratio of these two, so I'll take A dm times Vi, that's your signal, and then A Cm dm times Vi, that's your unwanted, or ideally this should have been 0. Then I get a ratio which is A dm times A Cm dm. So this is nothing but the differential gain of the system divided by the noise gain of the system. So this is the gain for the noise, because for a differential system, a common mode input is like a noise. So it's the ratio of signal gain, differential signal gain, to the gain of the noise. So this term we call it as CMRR, common mode rejection ratio. So this term we refer to as common mode rejection ratio. Okay. So a common mode rejection ratio, see, to say how good, how asymmetric a system is, ACM-DM suffices. Okay. But still, we should also mention what is ADM. Okay. We should also mention what is ADM. It is not an SNR per se. See, when I say signal to noise ratio, it is, you need to know what is the noise level and you need to know what is the signal level. Here, it's the ratio of two gains. It's not noise, signal to noise power. I just told you what was the reasoning for defining a parameter like this. So to explain the reasoning, I just said that in circuits or most analog systems, we define signal to noise ratio. Okay. So in the same way, we can define this is signal gain by noise gain. It's not signal power, but gain. It's a ratio of two gains. It's not an SNR. It's not an SNR, but it's like an SNR. Okay. The reasoning for that, I explained it using SNR idea. That's it. But this is not SNR by itself. It's just a metric to tell you how good your differential system is. Differential system is. SNR is a different thing, more different thing. Okay. Yeah. Fine. So the reasoning is that I can have two differential amplifiers with same ACM-DM. Two differential amplifiers can have same ACM-DM, but if ADM for one differential amplifier is much greater than the other differential amplifier, if ADM is, let's say, very small for one of the other differential pairs, then of course the one with the higher ADM is a good amplifier. So that's what this parameter is telling us. See, at the end of the day, what matters is not just the noise, but also the signal level. ADM tells you how much of signal is present in the system. ADM tells you how much of signal is present. And ACMDM tells you how much of common mode noise is present in the differential output. Okay? This alone doesn't suffice. You should also know how much is the actual signal content present. So therefore, a metric that would capture the common mode response of an amplifier better is CMRR, common mode rejection ratio, which is the differential mode gain divided by ACMDM, which is, I'll say, a common mode gain. Okay, common mode gain for in differential mode. Okay. So is that fine, or is it not clear yet? What is this? So I need to be very clear here. When I say SNR, signal to noise ratio, I am directly calculating noise. I need to know the noise power. Then I need to know the signal power. Then I say that, okay, I know the ratio of signal to noise, the value of SNR, signal by noise power. But if you see, yeah, so one of you, let me first clarify this. So if you need to calculate signal to noise ratio, you need to know signal power and noise power. But for CMRR, it doesn't depend upon signal level, but it only depends upon the gains. It's a property of a system itself. Yeah, ADM into VI is signal power. Yeah, signal level. It's a signal level. Yeah, see, the thing is that I derived it that way, telling you that you can take the ratio and you get this. But we don't know what the value of VI is. And secondly, it's in reality, you will not have same signal power at the input and same signal power at the common mode level. That will not never be the case. I just wanted to explain you guys that how the system will behave for differential and common mode inputs to derive this expression. Okay, yeah. So let me finish that point. So what I'm telling you here is that to calculate signal to noise power, you need to know the noise level and the signal level. But this is simply a ratio of two gains. Differential mode gain divided by ACMDM. And I told you an example, why will you need that, is let's say you have two systems, two differential amplifiers with same ACMDM. Their ACM DM is exactly the same. But ADM for one amplifier is much higher than ADM for the other one. It turns out that ADM for one amplifier is much higher than the other one. I can give you an example. So probably, I'll just quickly throw an example. So let's say we take a differential pair which looks like this. So you have so this current source here has a resistance of say 2 RCM. So this is I by 2, I by 2. So this is R here, R here. So can you tell me what is ADM for the circuit? What is ADM for the circuit? Ignore R naught, assume R naught is infinity. Can you quickly tell me what will be ADM for the circuit? See here, you can make one assumption. You can assume RCM is much greater than R. You can assume RCM is much greater than, yeah, I think one of you got it right. So you can just, can you tell me RCM is much greater than R? If you make that assumption, you get ADM as GM times R by 2 upon 1 plus GM times R by 2. Is that fine? This is your ADM for the circuit. GM R by 2 by 1 plus GM R by 2. What is ACM for the circuit? ACM? Again, let me just probably, okay, I'm sorry, so let me just give you a slightly different structure. Okay, let me just add the resistance this way. So this is R, this is R. So now I'll just make the modification in ADM. So this will be, ADM will be GM times R, yeah. So now this is your ADM for this circuit. Now can you tell me what is ACM? ACM for the circuit? Yeah, if you derive an exact expression, you will get GM will become GM by 1 plus GM into 2 RCM in parallel with R by 2. That's your GM times the drain resistance. In this case is R. But I just said that RCM is much greater than R, so this will reduce to GMR upon 1 plus GMR by 2. Now what is ACM? ACM again is ACM will be GM times R. Will this resistor come into the picture for ACM calculations? This resistor won't matter. So you will get ACM by GMR by 1 plus 2 GMR. And what is ACM DM for the circuit? Let's assume the differential pair has some mismatch. Differential pair for, no, let's assume it has some mismatch. If it has some mismatch, what can you say? It will roughly be whatever your ACM is here times delta GM by GM plus delta R by R. This is your ACM. Is that fine? So approximately ACM into this result. This is what you will get as ACM DM. Now we'll take another circuit. So another circuit happens to be this. So which is a current source with a resistance of RCM. So R and R being the load resistance. Now what is ACM DM for the circuit? We just derived it some moments ago. ACM DM will be AC. What is ACM for the circuit? For this circuit, ACM. It's same, right? You can split RCM, 2 RCM and 2 RCM on either sides. It will be GMR upon 1 plus 2 GM RCM. That's your same. It is the same as this circuit. So ACM DM will also be same. ACM DM will also be ACM times delta GM by GM plus delta R by R. That's your ACM DM. So ACM and ACM DM are same. But what about the AD, the differential mode gain for the circuit? What is the differential mode gain for the circuit? Gm times R. Gm times R. Now look at the differential mode gain for this circuit is Gmr by 1 plus Gmr, which is of course much less than Gmr. So which circuit is better? From a purely common mode rejection point of view, let me call this circuit 1 and circuit 2. Which one is better from purely common mode point of view? Second circuit, because ADM is much higher. So now if you see, both the circuits have same ACM DM, but ADM is much higher for the second circuit. Therefore, I can argue that the second circuit has a better CMRR, common mode rejection ratio. So therefore, the second circuit is better as far as common mode response is concerned. Okay, so that's fine. So we took an example to show the significance of CMRR. A common mode rejection ratio is nothing but the ratio of the differential mode gain divided by ACMDM. So we said ADM happens to be the differential signal gain, ACMDM happens to be the common mode gain for the circuit. Of course, output is taken differentially in both the cases. So for differential amplifiers, only differential outputs matter. And we said this is very close to like the definition of signal to noise ratio. We have to also take ADM into account. So just to give you a comparison, whenever if I give you signal to noise ratio as a very important metric, if I have two amplifiers, at the output, you know the noise levels happen to be N1, N2. That's your noise levels. It is given that N1 is less than N2. So you will think that noise level in the second amplifier is higher. Therefore, N1 should be better. But let's say you know this S1 signal power at N1, the first amplifier, also happens to be much less than signal power in the second amplifier. Then you can't say which one is better directly. You need to calculate signal to noise ratio of 1 and then compare it with signal to noise ratio of 2. Only then you can say which amplifier performs better or which amplifier's output has better quality, signal quality. So that is why ACM DM alone doesn't suffice. You also need to know ADM. Okay, so to tell how good an amplifier is as far as its common mode performance is concerned. So that's why we need CMRR, common mode rejection ratio. Okay, so we don't have to just suffice with ACM DM, but CMRR is an additional parameter which is needed to characterize or to say how good a differential amplifier responds to a common mode inputs. So what should be the ideal value of CMRR? From this expression, what should be the ideal value of CMRR? Infinity, right? So ideally you would want it to be infinity. And generally CMRR is expressed as 20 log of this in log terms. So it can be expressed as a ratio of two gains or 20 log of mod of ADM by ACMDM. So CMRR is often expressed as the ratio of, in logarithms as well. In decibels, it's also expressed in dB. So far what we have discussed right now, this is what we call small signal response. For small signal common mode inputs and for small signal differential inputs, we discussed how does a differential amplifier respond to them, both in the presence of mismatches and without any mismatches. Okay, so that's what we have discussed so far. So one of you are asking what form? See, CMRR generally it will be expressed in decibels. So we will explicitly express CMRR in decibels. Yeah, typically CMRR is always expressed in decibels. Otherwise, the units of CMRR will be volt per volt by volt per volt. So it's a ratio of 2 volt per volts. So instead, we'll directly represent it in decibels normally. No. See, again, when I said signal, I just gave you an example. How can one intuitively reason CMRR might have been derived? It generally doesn't mean. They are. Signal is same for both the systems. It doesn't mean that. Yeah. So those are the instructions we already discussed for the exam. When you are given we will generally, when we ask you to type the answers, we'll have to generally write it in volts per volts. Otherwise, for decibels, we will specifically ask you for voltage gains. Yes. But for CMRR, it's normally expressed in decibels. Yes. So one more question. Can we tell anything about SNR, signal to noise ratio, by the knowledge of CMRR? See, noise is a very generic term. Okay. Noise can include many things. Okay. So noise can also be because of random thermal motion of electrons in the channel of the MOSFET. And noise can also be noise from the supply. So you can't say that. You can't exactly say what is SNR from the knowledge of CMRR. They're two different things. I just told you how to look at it intuitively. Why does CMRR make sense? So to explain that, I compare it with SNR. That's it. But they are not directly related. So noise is a very generic term. I mean, noise can be because of MOSFET's thermal noise, which we will see next in the later courses how to characterize them. It can be noise in the supply voltage, or it can be noise in the previous amplifier stage. Everything, anything can come into the system. So that's noise. The knowledge of SNR will be for, I mean, the calculation of SNR will be a little bit more involved. But a CMRR is a system specific thing. It is independent of noise signal levels. It's purely a system, a differential amplifier specification. Like how ACM-DM is or ADM is, CMRR is also a similar kind of a specification. Okay. So now the next one, we discussed about large signal response of differential pairs to common mode and differential inputs. So first I discussed about how does a differential pair respond to common mode inputs, large signal common mode. So for large variations, so when I'm applying a large common mode change, we said for a voltage bias circuit, since source voltage is always fixed, your gate to source voltage keeps increasing if you increase both the gate voltages, so your bias currents increase. If bias currents increase, then we said the gain also keeps changing in the circuit. Okay, so that's how this circuit responds for a common mode, large signal common mode inputs. Then we said we took an example of a current bias differential pair and we performed a similar analysis. We increased the common mode voltage and we discussed what is the minimum common mode necessary, VICM minimum. So let's assume this current source needs a voltage of VOBI to keep it in saturation. See, because you have to keep the current source in saturation, you have to spend this much of voltage. If you have to spend this much of voltage, what is the minimum VCM necessary at the input? We discussed this in the last class. The minimum in terms of VGS and VOI, what is the minimum VACM necessary? Can I say it will be the minimum VGSQ? I mean, that's the quiescent VGSQ when the device is carrying a current of I by 2 plus V overdrive I. Okay, this is what we discussed as the minimum voltage necessary to keep both these transistors and the current source in saturation. And we said as you keep increasing both the common mode inputs, what will happen to the drain current in the circuit? Will the drain currents I1 and I2 change? I1 is the drain current in this device. I2 is the drain current in this device. Drain currents will not change. Drain currents will remain the same. If the drain currents remain the same, the drain voltage also remains the same. The drain voltage is VDD minus IR by 2. That's the drain voltage. So we said drain voltage also remains the same, and we said that follows from, directly it follows from the common mode response. Because ACM is 0 for the circuit, so both the drain voltages will not change. But we said as you keep increasing the gate voltage, at some point this transistor will enter into linear region. So what is the gate voltage for which it will go to linear region? So gate can go at max 1 VT higher than drain, right? So if your gate voltage goes a VT higher than the drain voltage, then this device will go out of saturation. So the condition was VDD. So it will be VDD minus IR by 2 plus VTN. This was the maximum voltage your circuit can go to. So then we said there is a range of voltages for which VICM, there is a range of minimum to maximum voltages for which the circuit will work perfectly. Yeah. So now the question is, no, see, when I say VI, any change in VI, that is nothing but any change in the gate. The gate voltage is still increasing here. Source voltage will also increase, but gate is also increasing, right? So since gate voltage is increasing, then the MOSFET has a chance of going out of saturation region. So the condition we said is this: V drain plus VT. When it goes higher than this, the device will enter into linear region. Of course, I mean VI is nothing but V gate. VI happens to be the gate voltage, which is why we are concerned about that. Okay. So then we said the voltage gain is independent of the common mode level. As long as you maintain your common mode level in this range and then apply differential signals on top of it, your voltage gain will be independent of the bias current. So that's what we said, which is another important and useful property of differential pair with current biasing. And we said that is the reason, for these reasons we said current biasing is the most popularly used biasing for differential amplifiers. Then finally, we discussed about, uh, I've also discussed about the differential response. How does the circuit respond differentially? If you apply a differential input, we said that let VID be the differential input that you're applying. This is 0. If the differential input is 0, what is the bias currents in the two devices for current bias differential pair? If I apply a 0 differential input, so which means both the voltages are at VCM and VCM. So then what is the bias current in I1 and I2? I am plotting I1, I2 here. What is the value of I1 and I2? I by 2 each, right? Both of them are going to carry I by 2 each. So I'll write I by 2, comma I by 2. So this is I1 and I2. Now I'm applying a voltage delta V by 2 here and minus delta V by 2 here. So I'm applying a differential voltage, but they are large signal now. As you increase delta V by 2 and decrease delta V by 2 on the other side, what should happen? Which should increase? I1 should increase or I2 should decrease? Increase. Which one will increase? Okay. So when you increase delta V here, I1 starts increasing, I2 starts decreasing. So I2 here starts to decrease. And we said there will be some voltage for which I1 becomes equal to I and I2 becomes 0. And what is that voltage? What is the differential input voltage for which it becomes 0? For which I1, the current is fully switched? We said the condition is root 2 times V overdrive. This V overdrive is measured when the current flowing through the MOSFETs is I by 2 and I by 2. This V overdrive corresponds to, so we can write your V overdrive, which is VGS minus VT, is square root of 2 into I by 2 upon beta n. Beta n is mu n CXW. So it will be root of I by beta n. After that, if I keep increasing delta, if I keep increasing the differential voltage, root 2 into V overdrive, yes, root 2 times V overdrive. Root 2 times V overdrive. So root 2 will be 1.414 times the V overdrive. Yeah. So now, as I keep increasing my differential voltage further, what should happen to the bias currents? What will happen to I1 and I2? If I keep increasing VID, because it cannot increase any further, so it will remain at I1, and this current will remain at 0. Okay, yeah, it will saturate, it will remain at I1 itself. Now let's do the opposite. I am going to apply minus delta V by 2 here and plus delta V by 2 on the other side. The exact opposite thing will happen. I1 will reduce and it will go to 0. I2 will increase and it will go to I. It will reach a value of I when the differential voltage is minus of root 2 times V overdrive. Okay, so this is the differential characteristics, large signal differential characteristics of a current bias differential pair. Okay, so you should get this graph, and the point where it transfers is this. And another most important thing is, I'll just take few minutes to finish this lecture. I1 minus I2. If you take I1 minus I2, what do you think will it be its value? What will be the maximum value of I1 minus I2? Subtract the two graphs. Subtract the two graphs, you should get you should get a graph that looks like this. So maximum will be I, minimum will be minus I, okay? And you have a graph which is VID versus I differential. So I1 minus I2, it's called differential current. I'll call it ID as the differential current. What do you think will be the slope of this graph? What will be the slope? What will the slope of this graph give me? What will the slope of this graph give me? The differential transconductance, right? The differential transconductance is still a transferred conductance, right? It's a differential transconductance. So what is the slope of the graph in these regions? What is the slope of the graph in these regions? 0, right? Even if the input is changing, there is no change there. So it will be 0 here. And if you see at the origin, you will have the maximum slope. So the graph will look something like this. So at the origin, when VID, when your differential input is 0, you will have maximum transconductance. The differential transconductance will be maximum at this point. Okay? And this Gm is given by dou ID upon dou VID. The differential current divided by the differential input. The maximum value will occur at VID equals 0. VID equals 0 is the maximum value of this Gm. Okay, so this is the graph you will be seeing in your labs as well. So you will see differential current and the differential transconductance. So typically we should operate your differential pair in this region, I mean in the region where your GM is nearly constant. So if you apply large signals, then your GM will keep reducing. So typically you will try to operate it in the small signal region where your GM can be quite high or the maximum value. I'll stop at this point. In the next lecture, we'll look at rigorous analysis of the large signal differential response of differential pairs.